Hi calculus student, this video is still chapter 5.1 by part 3. So we wrap up how to approximate area using left and right endpoints. And also notice the special features of left and right endpoints. I did not do this. I did not finish the last one, so maybe I'll go over the last one a little bit. It is for x squared minus x plus 2, and I didn't finish the right endpoint. I said that, I would start from starting from x1. This is f of x1, this is f of x2, all the way to x8, because I have 8 endpoint. x8 is 4, so x1 is 0.5, because delta x is 0.5. 0 plus delta x is 0.5. So then I use decimal to help me to get the list of f of 6.5, f of 1. So you can see if I use decimal, where is it? So it's over here. X squared minus x plus 4. So the 0.5 is 1.75. You add these together. This times 0.5, this times 0.5. All of these until 14 times 0.5. You add them together, you get that particular number, 24.5. And you can see the pattern. Okay, so I will do this in class. You can see the pattern that if in general I have f of x, and I'm doing under the curve. Okay, so if this is a, and then I have like x0 is a, and this is x1 and this is x2, dot dot dot, until I have xn, which is b is xn. So what happened is every single one, if x1 is what, a plus delta x, right? And in all these cases, delta x is equal to what? Delta x is b minus a over n. So to get a particular one, so x2 is a plus 2 times of delta x, because I have 1 delta x, 2 delta x, right? A0 is just a. So x0 is a. So you have this pattern. So if you do a right endpoint, you would see that right endpoint area is actually sigma I from actually 1 to n, because you're using the right side, and then f of xi. But xi is actually a plus delta xi, right? Because it's the I one, the first one is delta x times 1. The second one is a plus delta x times 2 times delta x. So this is the general form of how you do the right endpoint. Then for left endpoint, you can start from 0 to n minus 1, or you can say I equal to 1 to n, but f of a plus delta x times I minus 1. So this is kind of like the general formula. Let's look at the next page, the last part of the summation approximation is we estimate the area, but are they bounded? Do I know whether what is the lower bound of the actual area? What is the upper bound of the actual area? So it turns out that if the function is an increasing function, so that means it's going up. And let me make it a little bigger. If it's an increasing function, so I'll just do a picture here. So increasing, and I'm doing a few of these. So the left endpoint would be like this, right? This is the actual area, and it's always lower than the real one, the real area. See, the second one is a little lower. The third one, because this white area is actually belongs to the curve, but I did not use it. So, and then because it's increasing, the left estimation is always the lowest. So it would be the lower bound of the actual area. Whereas the right endpoint, so let's do it right. The right endpoint would be, I'm using this right side. So when I do it, so you can see that I use more than is actually on the graph, right? So I use this. I have some area that is over. It is an overestimate. It's always overestimating because the right side is always higher than the actual size of the curve. So the right endpoint sum would always be the upper bound. So you have a upper bound sum and a lower bound sum for an increasing function. Whereas for decreasing function is the other way around, right? So if you have a decreasing function, and then this is the left side. So if you do left endpoint, your rectangle is always over the real size of the area, right? Left endpoint. So you see how it is always overestimate. So your left endpoint is the upper bound. So we call this the upper sum. Whereas if you have the right endpoint, so this is a decreasing function, right? Your right endpoint is this one. If you do a rectangle like this, you use this as the height, you're always underestimating, right? You can see that you are always underestimating. So your right endpoint would be the lower bound. So only if they are consistently increasing or decreasing in that interval AB, AB. Doesn't have to be the whole graph is increasing or decreasing. In the interval AB, then you have a low endpoint and a right endpoint. If the function like fluctuate, then the left endpoint and right endpoint sum might not be the lower bound and upper bound. So the next things we're going to talk about is a new term called Riemann Sum, which is the end of 5.1, and we'll talk about a new concept in 5.2. So because we're always adding f of something delta x, so if it's in the left endpoint, it's x0, x1, x2, starting from x0, x1, x2. If it's the right endpoint, it's starting from x1, x2, something. So we call these kind of sum from 1 to n a Riemann sum. What Riemann sum does is you would partition your XAB into just like the partition that we talk about. So x starting from x0, x1, all the way in the middle, I have x and I minus 1, and then xi. So this is the I partition. And from xi to xi minus 1, I can pick any point here. I can pick xi, x star. So most of the time we pick the right endpoint. Why? Because it's easy to write. When you have the first one, it starts from 1. The last one is xn. So it's a nice number. So we call this, but technically we can pick the middle. We can take whatever that I want. So the one that I pick, this one, would be xi asterisk, xy star, xi star. So I would say each one I pick a number and I call it xi star, delta x. This, if I add this together, this sum is called a Riemann sum. Okay, you cut it into n. And then what is delta x? Delta x, you have to tell what delta x is. Delta x is b minus a over n. Okay, so this is actually just talk about how you add all those f of xi together. So, and Riemann himself actually had proved that if you take a limit where n approaches infinity, that means you keep on cutting until you have very, very big number of those small rectangle. It turns out that this will become the actual area under the curve. If, only if, if f is continuous and a non-negative function. That means your function is always above the x-axis. So this would just actually equal to the actual area under the curve. Okay, and we call it the Riemann sum notation of area under the curve. You take a limit of the sum of all those n rectangles. So you were just saying, okay, I'm going to go to 1000, find a sum. Oh, but I want my, not just starting and stopping at 1000. I want to go to 1 million of those rectangles. So if I add them together, it makes sense that they will be equal to the actual area. So that's the notation for Riemann sum. The Riemann sum is sigma I equal to 1 to n f of xi star. Usually we use the right endpoint, but it can be any point, times delta x. Delta x is b minus a over n. Okay, so we will look at this again in 5.2, and it's called Riemann Sum. So it can be used to find area under the curve when you take the limit. So that's why limit is very important, and it's limit to infinity.